Okay, welcome today. Today we're going to be covering the next part of Unit 5, and this is the last part of Unit 5. So we're nearly done Unit 5. You can imagine we're going to be doing that end of unit test coming up sometime soon. So today what we're going to be doing is it's the same thing. If any of you have done IGCSE chemistry, it's the exact same thing as the calculations that we did in IGCSE chemistry. So it's Unit 5.2. And what we're covering today is we're going to be covering bond enthalpy and some things that affect the bond enthalpy. So hopefully as a review, what you guys hopefully just hopefully you know this as review is that breaking bonds requires energy. And this is in every circumstance, is that, even when we've got those reaction graphs, which I hope some of you remember, you had your reactants, activation energy, products, you guys remembered, right? We always had this value right here, right? And we call that our EA. And EA was the activation energy. So basically what our activation energy is, it is the energy required uh, to start weakening the bonds. So weakening and breaking uh, bonds in the reactants. So that they can react to form the product, so that they can react to form the products. So if we took an example of, right up here, we could just say, carbon plus O2 reacts to form CO2. Gas, and these are all in gases too, or except for carbons in the solid state. So what we're going to have is this activation energy that we put in. What we're going to see is that we're breaking down O2 into two O atoms. So the activation energy that we're putting in is an energy that's proportional to the energy of an oxygen-oxygen double bond. We're causing this bond, we're weakening this bond. We may not break it. What we're doing, instead of having this really short bond length like this, we're putting in energy which is increasing the vibration. Right? We covered, or not we covered, but you will cover eventually, IR spectroscopy. And we know that these bonds are constantly vibrating in and out and in and out and in and out. So when we increase thermal energy, we increase this vibration. So instead of just doing a small little vibration in and out, we're doing a big one. So we're causing this to have a very short bond length, and the next instant a very long bond length. So we're destabilizing the stable bond. So that's what our activation energy is doing. Our activation energy, in our circumstance for IB, we just need to imagine that the activation energy is that we're breaking the oxygen-oxygen double bond into oxygen atoms. So we're breaking it up. The activation energy is proportional to the energy of this bond right here. So that is breaking bonds requires us to input some sort of energy. Okay, and then let's cover that in the opposite way. So 2, from the other side, is that forming bonds releases energy. So forming bonds release. So if we do that exact same example, right? Carbon plus oxygen reacts to form CO2 gas. So what we're going to see is that our activation energy is going to be breaking this apart into our carbon solid plus 2 oxygen atoms two free oxygen atoms in the gaseous state. And atoms by themselves are very reactive. They like having, like we said, they like having that complete orbital, basically. They like having that noble gas structure in most of the cases. So in this case, he doesn't have a noble gas, so he's reactive. So now he can react with carbon in order to form that carbon-carbon or carbon-oxygen double bond. So right now, this part to here is our activation energy, and this part to here is the enthalpy change. So that part right there is the energy from the top of the hill all the way down to the bottom. So activation energy is from here to the top of the hill. And then this one, the carbon reacting with the two oxygen atoms to form CO2, is from the top of the hill down to the bottom. And that's where we're going to get the negative delta H and release some heat in this circumstance. So bond forming is the part from the top to the bottom, and the activation energy is the part from the reactant up to the top of the peak. So we need energy to get up to that peak, but then once we got up to the peak, we have the energy to start the reaction. We release energy, we release more heat, which provides the energy for the activation energy, which activates more carbon molecules and causes that whole reaction to move towards the right, to move towards the products, move towards the product side. So forming bonds releases energy. So let's continue from this. So let's continue from breaking bonds. So basically, the stronger the bond, the bonds, the more energy that is required to break them. So if we've got a very, very stable molecule, like if we can just imagine like N2, right? Nitrogen is a rather inert gas, N triple bonded to N, but we can cause it to react, right? We can force it to react. You guys have done the Haber process. N2 plus H2 reacts to form NH3, reacts to form ammonia. So let me just balance this up right now. 3. Okay, so now it's balanced. So we can see that we can force this to react. But in the Haber process, we need special temperature conditions. We need special pressure conditions. And we need a catalyst. So we need 3 things to make this stable bond react. Whereas we know when we need carbon plus oxygen to form CO2, we just need a little match. We need a birthday candle, as it looks like I've drawn right here. That's supposed to be a match, but we can say a birthday candle. We can put it up under the carbon, and we can start reacting that carbon, that solid carbon, with O2 to form CO2. So it's much different reaction conditions. The N3 bond is more stable than the O2 bond, the O double bonded to O bond. It requires more energy in order to cause it to react. So the stronger the bond, the more energy that is required to make it react. So the more stable the compound, right? We can't really make something that's unstable and unreactive react. We can force it to react, but it won't react spontaneously like we see with lots of reactions. So 2, we're just going to expand on number 2 up here too. Forming bonds releases energy. So this is to continue. It's the stronger. Ooh, that's a nice color. The stronger the bonds formed, the more energy is released. More energy is released. So in this case, right, we form we have something unstable or less stable, and we react to form something very, very stable. So I'm going to do an example of this soon using numbers, but I don't want to do that now. This is just going to be the introduction to what we're doing today. So we're going to expand on that, don't worry. So just know that the stronger the bonds formed, the more energy that is released, will be released. And the weaker in contrast, the weaker the bonds formed, the less energy is released. And the weaker the bonds, the less energy is required to break them, right? We have, some sort of weak bond. So the energy required to break a hydrogen-hydrogen bond is less than the energy required to break an oxygen-oxygen bond, which is less than the energy required to break a nitrogen-nitrogen bond. So it depends on single, double, and triple bonds, and we're going to see that. Um, so number one, what we call this, I'll change the color back to the blue. So number one, what we call this is we call this the bond dissociation energy, and that is the energy required to break a chemical bond. So if we were to take something like, let me see, let's see what example I've got here on my sheet. Okay, so oxygen, it has a bond energy of 498 kilojoules per mole on average. So in order, the bond dissociation energy would be this number here. We have to put 498 kilojoules of energy in per mole of oxygen in order to break oxygen from O2 into the 2O, into its atomic or elemental form. So that's our bond dissociation. How much energy does this bond contain, and how much energy we need to put in order to shatter this bond into just two oxygen atoms hanging out. So okay, I'll take this off. I'll make a little bit more space. I'm going to make a little bit more space over here, and we can continue on over here. Ooh, that's going to take a while. There we go. So basically, what I want to talk to you about is that we've got something in our chemistry data booklet. This is again what you need to know. I'm going to put this in red because red is daunting and shows you that it's important. So in unit 11 or section 11 in your data booklet, what the IB introduces is they introduce bond enthalpy. So bond enthalpy. Let me see if I can get that data booklet up right here, and we can talk about it in a second. IGCSE chemistry data book, IB chemistry data booklet right here. So let's go down to section 11. Let's make sure it's the right one. Bond enthalpies, page 11. So let's go to page 11, and we got bond enthalpies right here. Let's just look at this down here just as an example. So I'm not going to save this. I'm just going to comment right on here, right there. So what these are, right? A carbon-carbon double bond. What this is, the value that they're giving you here is the average. Yeah, I know this is a fancy new trick, right? I can write on PDFs now. It's the average bond energy of a carbon-carbon double bond. But what I want you to imagine, though, this is average. So what we're going to see later on is that we can compare this bond energy. So we can take let's do an example here. Let's do ethene combusting with oxygen to react to form CO2 and H2O. So we can do this in two ways. We've got in your data booklet, you've got a section on enthalpies of combustion. So you've got a section on enthalpies of combustion. So what that'll be is it'll be something like this. It'll be something like C2H4 plus O2 reacts to form CO2 and H2O. It'll be balanced, of course. They're a lot less lazy than I am. but, but basically, it'll have your delta H of combustion equals negative something kilojoules per mole. Or you can calculate the delta H of combustion by using these bond enthalpies right here. We can calculate, we can take a carbon-carbon double bond, 614 kilojoules per mole, add 4 carbon-hydrogen single bonds, add an oxygen-oxygen double bond, and then a carbon-oxygen bond here, a hydrogen-oxygen-hydrogen bond here, and we can add them all up, and we can do one versus the other. We can do delta H of bonds versus delta H of combustion. And what you're going to find out is that these values are not equal. And the important part, the whole reason why I just talked about, you can calculate this in multiple ways, either through your bond enthalpies or through the combustion data. And why this is that this is an average, right? In most circumstances, we've got a carbon-carbon double bond has this bond strength. But what you should know is that this bond strength is not equal to this bond strength, which is not equal to this bond strength. So it depends on the circumstance. It depends on the molecule. So what they've done and what scientists have done is they've just said, okay, on average it's 614 kilojoules per mole. If we want to do a raw calculation, if we just want to guesstimate. So if we want to get a good estimate of what it might be theoretically. But the data, the enthalpy of combustion, this is the important part. This is experimental data. So it's the true value done in a calorimeter, calculating the heat or the delta H, the enthalpy change of combustion of ethene in a nice molar ratio of oxygen. So they've done it, the real conditions. So it's not the average, it is the real. So if you get the option to use the enthalpy of combustion or calculate the bond enthalpy, you always want to use the enthalpy of combustion to get the value, because it'll be the real experimental value. Okay, so let's continue on there. That was the important part. The data booklet, the bond enthalpy, this is the average value of the bond strength, but also the weakness is that it is the average value. The weakness is that it's the average value, and the average is not always representative. Like you, right? You could be scoring a 7 in IB chemistry, but the class average is a 5. So you know that the average is not representative of you, right? You can be getting a 1 and the average is a 5, but the average is not representative of you. It's representative of the overall grades in the class based on performance, but it's not representative of the exact situation that you are in. So it's the exact same in this case. It gives you, it gives you a solid, you can assume it's close. Assume it's close to most values, but there are going to be outliers. There are going to be exceptions. So with this, right, the average is a weakness in this circumstance. Okay, so let's do an example here. Let's try to calculate this. So in this case, let's show you why this is real. So let me erase this. I'll show you why you want to use the enthalpy of combustion rather than the bond enthalpies. So, okay. Sorry, this takes a second to erase all of this. Uh, there we go. Okay, so let's take that reaction. I like doing it because I've already done the calculation in advance. Carbon plus oxygen reacts to form CO2. Okay, so we're just burning coal at this point. I'll put the states in. So remember, never forget your states. And this is basically just something I want to teach you guys. It's just always write the state. Unless the question explicitly says do not write the state, always write the state. Because maybe you won't get any points go up, but at least you won't lose any points because there's no state. It's better to be safe, or, oh no, your grades went down, now you're sorry. It's better to be safe than sorry, right? Always write down the states if you know the states. So, okay. So let's go from here then. So carbon, right, it doesn't have any bonds here. So it's got a bond enthalpy of 0. Oxygen, how would I draw out the molecule is O double bonded to O. So let's check the bond enthalpy. The bond enthalpy, let's just scroll up. Let's just, where is it? O2, 498 kilojoules per mole. So in this case, we've got 498 kilojoules per mole. Carbon. And then we're going to react to form CO2, which is 2 carbon-oxygen double bonds, which is 2 times carbon 804. 2 times 804. So let's try to logic our way through this, right? In order to break this bond, we have to put in 498 kilojoules per mole. So our delta H, right? If we have a negative delta H, that's energy coming out. A positive delta H is energy going in. So we've got positive 498 kilojoules per mole because we needed to put the energy in. But then we're forming bonds. We're forming carbon-oxygen bonds, which means that whenever you form a bond, energy is released. So we minus, because we're releasing energy, 2 times 804. So our delta H value, let me get my calculator right here, is 498 minus 2 times 804. So our delta H value for this combustion reaction is negative 1110 kilojoules per mole. Okay, so this is calculated based on bond enthalpy. Okay, so now you can see that's what we've calculated based on our bond enthalpies. Now let's compare that to our combustion data. Let's go to our data booklet. You got to learn how to use this. I got to learn how to use this too. Enthalpies of combustion, page 13. Let's go to 13. Enthalpies of combustion. Rotate. There we go. Enthalpy of combustion of. Let's see. Ethane, propane, methane of carbon, negative 394 kilojoules per mole. Let's see where we might have went wrong here then, because this seems a little bit off. Negative 394 kilojoules per mole. So let's see where we could have had a little bit of an off value here. Carbon 498 minus 200, 16, 12. Seems close. Give me a second. Um, 346. So yeah, in this case, we can't really even compare them, right? We can't compare carbon in a standard state, just a carbon atom. We assume it's not bonded to anything else. It's just ground down, so that's why we don't have any bond enthalpy. But what they did here is that they assumed it was, oh, sorry, no. They assumed it was graphite. So graphite has different bonds, so we're going to have different bond enthalpy, right? So I assumed it was just carbon completely by itself, but the combustion data assumed it was graphite. And with graphite, we know we've got carbon, carbon, carbon bonded to 4 different carbons. I assumed it was just elemental in this case. So just carbon atom by itself. So that's we're going to have a difference in our data because of that. Because in this case, we assume that we didn't have carbon bonded to other carbon atoms. So that's why there's a difference in the data here. But let's see if we can find a way to kind of balance this out so that we can figure out. So let's see, 1, 2, 3, 4, 5. Let's put just a 5 here. Let's try to continue. A 5 here, which means we need a 5 here, which means we need 502. We need also a 5 here. So we've just increased it. So now we've got carbon bonds. 1, 2, 3, 4 carbon bonds, single carbon bonds in graphite. Not graphene, because graphene, right, has that, again, hexagonal structure. It's got some double bonds in there. So give me 1 second. So actually, yeah, I don't even want to compare these two because we can't really compare reacting elemental carbon. We would have had to compare graphite. So let's see what we can do. Let's try to do a different one in this case. Let's try to do methane right here. Let's try to do methane just to make this a little bit of a better example that's more comparable. Because we can't compare graphite with elemental carbon, and there's no combustion data for elemental carbon. So let's just redo this calculation part. The calculation will be done in the exact same way though. So how this calculation is done is CH4 plus O2 reacts to form CO2 and H2O. Let's make sure this is balanced. We got to double this. We need to double this. And now we're balanced. Good. So let's draw this out. C, H, 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 H. 2O2, so 2 times oxygen, oxygen, reacts to form CO2 plus H2O. 2 times this. So let's see what this is. We got a carbon-hydrogen single bond. We got 4 carbon-hydrogen single bonds. So what that is, we got to go back up to our last page. Let me just try to rotate this back. Carbon, hydrogen single bond. Okay, so carbon bonded to hydrogen is 414 kilojoules per mole. 4 times 414 plus 2 times oxygen, oxygen double bond. That was right down here. Oxygen at 498. 2 times 498 reacts to form 2 carbon-oxygen double bonds. Carbon 804, 2 times 804. Sorry, 804 plus 2 times 2 oxygen-hydrogen bonds. We've got to go up. Oxygen hydrogen bond is 463. So 2 times 2 times 463. So then we can calculate this. These are bonds that we have to break, right? We need to make that carbon hydrogen react to form individual carbon and hydrogen bonds. This is the energy we have to put in. So delta H of the reaction is, let's do this math. 4 times 414 is 1656. 1656 plus 2 times 498 is 996. Those are the bonds that we have to break. And then we're going to release energy over here. So we have to do minus 2 times 804 minus 1606 minus, and then this value, 2 times 463 times 2, so minus 1852. So delta H of a reaction is equal to 1656 plus 996 minus 1606 minus 1852. So we get an enthalpy of combustion of negative 806 kilojoules per mole. And this is calculated using bond enthalpies. So let's see what the real value is. Let's go back to the data booklet, page 14 right here. You just got to rotate it. And of methane, negative 891. So delta H of combustion is negative 891 kilojoules per mole. So you can see, right, the bond enthalpies misjudge this. So let's see by how much. 891 minus 806. Somewhere we've gained 85 kilojoules per mole of energy. We've released more energy from the combustion data than we have from the enthalpy data. So this is the effect that the average has on it, right? The average carbon-hydrogen bond has this much bond strength. The average oxygen-oxygen bond has this much bond strength. The average, but it doesn't take into account the actual experimental circumstances. It doesn't take those into account. So okay, so let's I'll end here right now. What we're going to do is we're just going to do a quick, I'm going to show you what the equation is then, and then we'll continue on in the next video for things that affect bond strength and bond length. So delta H of reaction equals the sum of the bond enthalpies of reactants minus the sum of bond enthalpies of products. So the delta H of reaction down here, it's this right here. What it is this is the energy input to destabilize reactants. It's the energy input to break, right, like we did O2 into 2O. It's the energy input. In a way, it's kind of like the activation energy of the reaction. How much you need to put in to break these bonds. And then this is the energy released by bonds forming. So okay, now I'm sorry about that first example. I thought there was combustion data on that. There wasn't. I can't compare graphite, right? Graphite, we can't compare it to elemental carbon in this case. But most of the time we are dealing with graphite, so we could redo that calculation with graphite. But in this case, we did it with methane instead, and hopefully we reach the same objectives. So hopefully this video was useful. I will see you next video soon. I'm making that video right now.